Welcome back, friends. We're going to talk some more about curvature and normal vectors for space curves. So let's just kind of review, pull together some of the things that we already know from previous lecture videos. So if we are given a vector valued function, we call that guy the position vector. We call him R of t. And then we use S, not a vector. S is the arc length parameter of the curve. We also know we can find a unit tangent vector. We call that guy capital T, which is the derivative of position with respect to the arc length parameter, or velocity divided by the magnitude of the velocity, those both being vectors as well. We've got information about curvature. Curvature kappa is the derivative of the tangent unit vector with respect to the arc length parameter, or more simply, which requires less work, we don't have to parameterize the unit tangent vector. We say the magnitude of the velocity vector, 1 over that magnitude, times the magnitude of the derivative of the unit tangent vector with respect to t. And remember that dt ds is orthogonal to t. So we're looking, when we think about orthogonal, we're talking about that principal unit normal vector. And we call that guy n. N is equal to 1 divided by kappa times that orthogonal vector dt ds, or more simply dt, the derivative of the unit tangent vector with respect to t, divided by its magnitude. All right, so we've got a lot of information that we know how to use. So let's do an example where we find the curvature of a helix. So we're going to find the curvature of a vector in 3 space. Previously, we did one in 2 space in a xy Cartesian plane. In this example, we're going to find the curvature for this helix, r of t. So component A cosine ti plus component A sine tj plus btk. We know that A and B represent greater than or equal to positive real number values, and that A squared plus B squared cannot equal 0. So first thing we're going to do is we're going to calculate our unit tangent vector, which means we need our velocity vector. The first thing we're going to do is we're going to find t. In order to find t, I need v, which the derivative of a cosine t, the derivative of cosine is negative sine, so I've got a negative sine t I. The derivative of sine is positive cosine, so a cosine t j, and the derivative of bt would be b times k. The magnitude of this, the magnitude of v, is the square root of a squared sine squared t plus a squared cosine squared t plus b squared. And if I factor for these two terms, if I factor out sine squared plus cosine squared, got the a squared in front, that's going to become a squared times 1. So we end up with the square root of a squared plus b squared for the magnitude. So that means t, my tangent vector, is negative a sine t I plus a cosine t j plus b times k. And so all of these terms are then divided by the square root of a squared plus b squared. So moving forward, after we find t, we're going to find curvature. But in order to find curvature, we need the derivative of that unit tangent vector. So dt, dt. And if you think about this, remember a and b are constants, right? All these a's and b's represent numbers. So I could have this factored out in front and say 1 over the square root of a squared plus b squared, and that would just be a constant coefficient. So I don't have to use the quotient rule here to find the derivative. I'm just going to differentiate each of these terms. So the derivative of negative a sine t, that's going to be negative a cosine t I. Cosine, that will become negative a sine t j, and then the derivative of b, since it's a constant, will be 0. So I have 0k all over the square root of a squared plus b squared. So this is just like a constant coefficient, 1 over that. All right, so the second step here is we're going to find curvature. Curvature, kappa, is 1 over the magnitude of v. So that's 1 over the square root of a squared plus b squared times the magnitude of the derivative of the unit tangent vector with respect to t. So we've got the magnitude of negative a cosine t I plus negative a sine t j divided by the square root of a squared plus b squared. Now I have times a in front of both of these, so I can factor that out, and the magnitude of a constant is just the constant, so that a can come in front. And the same here, this is a constant, so I can factor that out of these magnitude bars, and root a squared plus b squared times itself is just going to be a squared plus b squared. So I have kappa is a over a squared plus b squared, and then we have the magnitude of negative cosine t I plus or minus, however you want to write that. We'd have negative sine t j. And of course, the magnitude here, that's going to be the square root of negative cosine t quantity squared plus negative sine t quantity squared, which is the Pythagorean identity, which is the square root of 1 or 1. So my curvature, k, is a over a squared plus b squared. So I've brought in here the picture, which really represents this helix shape that we're talking about. And our curvature is a variable equation based off the a's and the b's that were coefficients in our position vector function. So these a values, these are helping us or determining the radius of this circle, and then the b is determining, how fast we're vertically increasing. So we can do a little bit of analysis with this curvature to kind of show the different kinds of helices we could create. So for example, if we had a fixed A value, meaning A doesn't change. So looking at our curvature equation, we would always be getting a larger denominator. So if we have a fixed A value and the B increases, we'd have some constant divided by a value constantly getting larger. So if you're dividing by a bigger value, that would mean that the curvature would be decreasing. Similarly, we could look at, well, what if we had a fixed B value? So B's down here in the denominator, it's fixed. And so if we looked at decreasing A, and these were becoming smaller and smaller values if these were changing. So fixed B, A decreases. What does that tell us? That would eventually decrease the curvature because we would end up with a small number here divided by a larger B. So that would be also a situation where the curvature eventually decreases. We have two other situations we could look at. We could say, well, what happens if B was equal to 0? So if B is equal to 0, then that means there's no vertical change, and this would just be rotating around. This would be a helix, would turn into just a circle of radius A. So it would not be moving up in that 3 space. It would stay in that XY plane. And lastly, we could come over here and we could say, well, what happens if A were to equal 0? So if A were to equal 0, this circle that the helix is revolving around would have no radius. And so essentially, this would just be a 0 radius circle traveling up the z-axis. Or rather kind of just a line, a dot. All right. So, this is a dependent equation that we have for curvature, and it depends on what the A and B values are in that initial helix given by our position vector. So I hope that helps you understand curvature just a little bit more. I'm going to do one last video following this. As always, email me if you have any questions.